Hello there, and welcome to the first review session in a series of 5 that I'm going to be recording for you all in preparation for your combined aviation PC, which is your culminating exam that you need to pass in order to succeed in level 4 and proceed to level 5. This is theory of flight, the first of 5 topics that will be covered. The other topics are, so we have theory of flight, meteorology, navigation, air law, and engines. Each lesson is going to be, well, each review session rather, is going to be about 30 minutes that you can go over at your leisure to review these slides here. These are not necessarily, I won't necessarily touch on absolutely everything that will be on the exam, and not absolutely everything that I mention here will be on the exam, but these are just good resources for you to follow and review and make sure that you understand all the key concepts, because that's what's most important here. So without further ado, here we are with our theory of flight class. So to start with, it's important to know what airspeed limitations are. So as you can see from the slide there, the definition of airspeed is the rate of movement of an aircraft relative to the air mass through which it is flying. So that's a whole bunch of words to basically say it's talking about how fast the aircraft is moving through the air, not relative to the ground. If you're flying at 50 knots directly into a 50-knot headwind, both of which numbers are not very reasonable, then according to the ground, you would be going nowhere, but your airspeed is 50 knots. You are still traveling, you're traveling at 50 knots through that air mass. Causality, so what causes it is thrust, and it gets impeded by drag. So if you remember your couples for the 4 forces of flight, you have thrust acting in one direction, so for example to my right, and then you'd have drag that acts in the opposite direction. So as you can see there, there's a few different ways to balance it, including your pitch attitude and your power settings. So the more power you put in, the more thrust you're going to have. And depending on how you're angled, you could be generating more lift, which means you have more drag, which will counteract your thrust, for example. VSpeeds. So there's a whole bunch of these, and it is important to understand what they mean. They're all abbreviations, and you can find many of them on your airspeed indicator in the aircraft. So just these are the very important ones. There are a lot more than this, but these are the really important ones. So VNE is when you're going to hear a lot, especially if you go on glider or power. It is the speed you cannot exceed in that aircraft. If you do go past that speed by any amount, or even really if you get close to it, just for the sake of safety, that aircraft must be brought in for a maintenance check to verify its structural integrity, because if you go to that speed or beyond it, you could very well compromise the entire structure of the aircraft. So obviously flying sustained beyond that speed is not going to be a good idea while you're in flight. If you do end up accidentally passing it or intentionally for a small period of time, well, it doesn't matter how long it did exceed it for, you need to bring it in for servicing. Normal operating speed. So again, just reading off the definitions here. So it's how fast the aircraft is designed to be traveling through the air at cruising speed. It's also how fast you can go while you're still in normal category. So if you remember from your other classes, there are several categories, which are normal and utility and aerobatic. So if you're in the normal category and you're not certified for utility or aerobatics, you can't really exceed this speed. It's not the VNE, but VNO, as in no, stop what you're doing, don't go past it. Maneuvering speed. This one's pretty straightforward. When you're conducting any sorts of maneuvers, which can be anything from a full stall or anything, to even just operating your flight controls to full deflection. So your rudders all the way to either side, or pulling the yoke to move your ailerons all the way to the left or to the right. You cannot be at or beyond this speed with full deflection because you risk damaging those control surfaces. Maximum gust intensity. So when you're flying in turbulent weather, and you can expect gusts, and they may be from an unpredictable direction, then you can't exceed this VB, which is your max gust intensity speed, because that gust could bring you up to or past VNE, which obviously isn't good and isn't safe. VFE is similar to maneuvering speed, but don't confuse the two. You'll notice I listed the rudders and the ailerons for the VA, the maneuvering speed, and I should have listed the elevator as well. The flaps are separate. The flaps are usually mechanically operated. Sometimes they're pulled by hand, but flaps are different, and the speed is generally quite different for the VFE compared to the VA. And you need to be very, very careful with that because breaking your flaps isn't good. They're very important for landing in a powered aircraft, though it can be done without them. Mach number. So if you've gone through high school physics classes, you'll know that Mach number is basically how fast you're going compared to the speed of sound. Since the speed of sound varies based on the temperature of air, so if, for example, if you're flying in hotter air, then sound is going to travel more quickly through it. Sound also travels more quickly through water than it does through air. You can just kind of think about that as a density thing. As for the Mach number itself, you can just find it's a pretty simple calculation. You divide the speed of the aircraft by the speed of sound in the current temperature of the air mass you're in. I would hope you're not flying inside a body of water. So you can see there, that's a pretty good example that's written there about you're going 85% the speed of sound would be Mach 0.85. That's pretty easy to think about. This one isn't a complicated concept. If you're going Mach 1, you are going the speed of sound. If you're going Mach 2, you're going twice the speed of sound. It's reasonably straightforward. Next, flight instruments. So I've referenced a couple of these. The Airspeed Indicator is a big one. These are instruments. They're not flight instruments. Just trying to keep it entertaining. All right, pedostatic instruments. So these are instruments that are connected to the pedostatic pressure system. In a glider, you have a pedostatic tube, which is one tube. It's got kind of two entryways. One of them will take static readings, and one of them will take the dynamic readings through the pedo pressure tube. And on most powered aircraft, you're going to have a pedo tube mounted underneath the wing, and you'll have a static port that's mounted generally to the side of the cowling or near the actual cockpit on the fuselage of the aircraft. As I'm sure you know by now, there's a reason that they're taken from different locations, and that being that the ram air is needed for the pedo tube to find out how fast the air is entering and what that pressure change is. And then the static port is supposed to take as close to an ambient reading as possible. So if you weren't moving, if you were just kind of floating there in the air, what's the temperature and the ambient pressure of the air at that point? Obviously, you can't get exact readings, but you'd be surprised at how good the static ports can be, like in a general ballpark. So if you can take a look at this diagram here, I'm not sure if I can do. I don't have a way to do my. Oh, there we go. We've got a laser pointer. All right, so we have the airspeed indicator, we have the vertical speed indicator, and we have the altimeter. You can see that all three of these are connected to the static port. All three of these must have the static port to operate. But the ASI is the only one connected to the pedo tube. So that tells you just about all you need to know about that, which is that the altimeter obviously doesn't care how fast you're going, because you could be moving that fast in any direction, but you need to be, all it cares about is what the current pressure is. And since you set your altimeter on the ground, it will know what the barometric pressure is at surface level, and it will be able to tell you what your altitude is ASL, so that's above sea level. VSI is much the same. It just takes the change in ambient pressure. So if you go from, let's say, 3,000 meters and you suddenly descend to 2,500, it's going to read that pressure change and tell you you were descending at this rate. So going down this many hundreds of feet per second usually. The ASI, on the other hand, needs to know what the static pressure is, so what the ambient pressure is, and then compare it to the pressure being put into the tube, into the pedo tube, to find out exactly how fast you're going. Because that ram airflow, it's very aptly named. That ram air is literally the force of the air being rammed into the pedo tube, which generates that pressure, which it can then compare. That's just the simplified description. You can see also it says alternate static source. Don't worry about that. Some aircraft have them, not all of them do. Generally gliders don't, but but in general powered aircraft would. Altimeter. The picture is a long story, and we're not going to explain that because this lesson was meant for something else. For the altimeter, it's going to indicate the altitude of the aircraft. So each one of these slides, just for reference, is just going to go a little bit more in depth. So I explained their purpose. This is going to be exactly how they operate. So it's going to be consisting of a stack of aneroid capsules. That's an important term that often comes up on exams, and they are as close to a vacuum as you can get within reason without big fancy equipment. And the atmospheric pressure that is allowed into the capsules allows them to expand or contract depending on that relative pressure. And so think of it as like an accordion. It's a whole stack of them. And as they contract or expand, they're going to move upward or push against these gears that will then turn the dial of your altimeter. It's a pretty cool system. So if you want to take a look here, I'm not going to spend too long on it, but this is a stack of aneroid. This is an aneroid capsule here. And basically as it expands, it's got that link here to this. To the dial itself. So as that expands, it's going to push down, and it's going to cause this to rotate. Something important to notice is that this blank area here is 100% vacuum. There's not 100%, but it's very, very close to an absolute vacuum. And they try and keep that way intentionally. Altimeter errors. So altimeters are prone to errors, just like every instrument is. So the way you need to know how this works is that as you fly long distance flights, especially from one area to another, they can have different ambient pressures at ground level, and you need to adjust your altimeter accordingly. So you need to be aware that when you fly from an area of high pressure to low pressure, be aware that your altimeter is going to overread. It's going to tell you you're higher than you actually are. So because of that, it's important to take a look below you and check your actual altitude. And that's why we have the from high to low, look out below. And then the opposite will happen if you fly from low pressure to high pressure. Your altimeter is going to underread, and so we have the expression from low to high, clear blue skies, which is essentially to say it's not that big of a deal. You still need to be aware of it because you need to be flying at the right altitude, and there's certain regulations and everything, but you're not at risk of crashing into the ground by flying a little bit too high. So yeah. Calculating this error. So continual heating and cooling of the atmosphere means that the temperature is very, very rarely actually what we consider to be standard temperature. So if you remember from your IKO what that temperature is, I'd recommend checking your notes if you don't have it already. That really doesn't occur very often, just in a few months in Canada, and it can be hard to dictate that otherwise. Density altitude is going to correct for temperature errors. So in order to do that, you need to take your pressure altitude and you need to add 100 times the difference of your two temperatures in degrees Celsius, and that will bring up your altitude in feet. Airspeed indicator. All right, so this is the one that's connected to both the pitot tube and the static port, and you can see these two connections are happening here. So we have this diaphragm, which is an aneroid capsule, and you have your ram airflow that comes in through the pitot tube and connects to the diaphragm there. And there's a whole bunch of lever systems to get this to work properly. And you can see this is designed to get a lot more rotation out of a small amount of movement to make it easier to read. But essentially what this means is as this expands outward, it's going to cause, or contracts inward, it's going to cause movement through this whole fancy system, again, comprised of a vacuum because all of that air pressure just goes into this capsule here. And that's going to cause movement of these hands here. Yeah, so important notes are that it is the only standard instrument connected to both the pitot and static pressure sources, and it checks the difference between them. I say checks because that's just the easiest way to say it. There's some complicated math behind it, but you don't need to know that for your exam. So this is going to show the indicated airspeed. That's important. It's straightforward to hear out loud. The indicated airspeed is the airspeed that gets indicated on here. It's what you read off, and you need to make corrections to it in order to make sure that those get made correct, get changed into your actual airspeed or your ground speed as necessary in flight. ASI markings. This is what we talked about previously. So we know what the VNE is. That's this little red line here. Yellow range is right where it starts is the VNO, which, if you remember, is the normal operating. So you shouldn't really be flying in this yellow zone. In general, it's not a very good idea. If you end up in it for a small period of time, that's fine, but don't intentionally cruise at 180 knots on the aircraft that this altimeter is designed for. The green is obviously the normal operating range. So here at the end of it is where the power off stall speed is. So you will stall no matter your angle of attack below this speed when your flaps and your gear are up. You can see there's this extension of the white arc though, and that's essentially the same thing as the end of the green arc, but with the flaps. So this is where you would stall with your flaps down. This is where you'd stall with the flaps up, and this whole range is what applies there. All right, so I mentioned converting between different airspeeds. So this is how to go through this. So an easy way to remember it is ice tea. The pretty cool drink. It's just a mnemonic to help you remember. So this is directly what you read off. It's pretty straightforward. It is what's on the dial. It's the information you interpret. Calibrated airspeed. So you take the calibrated airspeed and you correct it for your instrument error. And any error that happens from the airflow through the pedostatic system. So to get from indicated to calibrated, you need to correct for the instrument error. To go from calibrated to equivalent airspeed, you need to account for compressibility. So this is really important when you're talking about high-speed jets, but general aviation aircraft, not really important. Doesn't really come into a factor. And from equivalent to true airspeed, so as I mentioned, the actual speed that you're traveling through the air, which is what you need in order to calculate your ground speed, as long as you know the wind speed as well, is that you're going to have to correct for your indicator error, for density and temperature. Yeah, so as you can see here, I did include a little note about how you can get this from calibrated or equivalent. So you can, and that's just because, as I mentioned, it's not important in general aviation aircraft, so like the Cessnas and things that you'd be flying on power. So here's the way to think about it. It's not my favorite mnemonic because position doesn't really help give you an indication, and same with compressibility. Density is something that you do know, but these steps in between aren't my favorite. So I would recommend just remembering you're correcting instrument error and compressibility, which doesn't really matter in your general aviation aircraft, though I can't say that it wouldn't be on your exam. I'd imagine that the process here will be. So ICET, and with the pretty cool drink being position, compressibility, density. Vertical speed indicator. If you've had a class with me before or you've been to the gliding site with me, I don't like this instrument. Most pilots don't like this instrument. It is very slow. It is often inaccurate. It's just there basically to tell you if something's really out of whack. It's not the most helpful because of its very large delay, which I'm just going to kind of skip down to the last point here, which is that it's got a 6 to 9 second delay on average for it to actually react. So let's say you're going hunting for thermals in a glider, and you kind of feel something and you're not sure if it's a thermal, so you keep flying in a straight line, and then all of a sudden you notice this jumps up to 1,000 feet per second. And you realize, oh, well, I guess 6 to 10 seconds behind me there was a thermal, and you're gonna have to loop around and go back. When really it's better to just rely on that feeling, that like literal gut feeling that will help you while you're on glider. Anyway, this instrument is connected to the static pressure system. So the atmospheric pressure travels through the static port into the aneroid capsule. And as you can see just down here, I'm not sure if it's blocking it off with the zoom thing, but there's a calibrated leak right here. So they intentionally leak out air through the capillary tube, which is this, into the casing. So unlike the other instruments where it was a vacuum. So the difference in pressure is going to cause this capsule to expand or contract, same premise as before. And then you can read your airspeed or your vertical speed on the dial. Gyroscopic instruments. So there are a few of these in the aircraft, and it's important to know how they work. So as this slide states here, they're useful when you're flying VFR, which is visual flight rules. You're just looking outside the plane and that's how you fly. They are mandatory for flying with instruments. So IFR is, if you remember, flying, you could fly it completely blind. You could fly through a cloud, not be able to see anything outside of you. And that's true. Once you enter a cloud, there you have zero visibility. I did that once on glider with my instructor, and it was an interesting experience. Anyway, so these instruments are going to use gyroscopes, which is a little spinning wheel on a gimbal, which is going to help make sure that it stays in the same orientation no matter how you turn, to help give you some relation. There's two things you need to be aware about. Gyroscopic inertia is basically any rotating body. Once you set it spinning, it's going to maintain that plane of rotation. So it's going to continue spinning in the same direction. That's why a spinning top works. Precession is something where if you're rotating something at 90 degrees, it's going to have a natural tendency to rotate around its other axis at the perpendicular. And it's hard to kind of demonstrate like that. But if you've got a rod here and you've got this, and let's say there's a wheel attached to my elbow, kind of like in this orientation. So it's spinning like this. What's going to happen is that it's going to want to rotate like this in addition to the wheel itself spinning. That's just some cool physics stuff. You don't need to worry about how that happens. You just need to be aware of what precession is and how that applies to its given axis of rotation. All right, so we've got a few different types of power sources. So we have engine driven. So basically a vacuum pump, which is a cool piece of machinery that will evacuate all the air from the suction, will create suction, and it doesn't create a perfect vacuum. It's a partial vacuum, and this allows the air to rush into the system, which pushes the gyro wheels around and causes them to spin and make sure that they keep spinning at a constant rate. Venturi tubes are excellent tools to help create a vacuum. So they take advantage of the airflow of the propeller with that low pressure area to create another partial vacuum, and that does the same thing with the airflow in order to propel those gyroscopic instruments. IFR planes and aircraft tend to use electrically driven gyros. So this is where they just rely on electricity to keep those gyroscopes moving at the right speed. And as you can see there, we get alternating current from alternators, which are designed to take a little bit of power from your engine as you're flying in order to keep your various components alive, or dedicated generators to drive them. These tend to be very small and therefore not very power consuming. Anyway, as this says here, common practice is to have both of these systems in case one of them fails. It's pretty straightforward. It's an extra safety measure. You don't want one of your most important instruments to fail while you're flying at 20,000 feet. All right, heading indicator. Heading indicator is otherwise known as the directional gyroscope. It essentially functions like a compass. It's going to tell you the direction that you're heading. However, it's susceptible to that precession error that I mentioned before. In fact, it's so susceptible to it, you need to be actively aware of it, and you need to correct it every usually 15 minutes or so in flight. You need to fly a straight heading, check your actual compass, make sure there's no deviations on your actual compass that might be affecting its reading, and you need to input your you need to change the dial on that heading indicator in order to make sure that it's reading correctly still. So you can see it's moving very fast. For reference, the propeller of a Cessna 172 usually operates between around 1,500 and 3,000 RPM. And this here is going at 12,000 RPM. So it's moving very, very quickly. This is the gimbal here, if you're not familiar with it. And this is going, as it moves like this, it will accordingly turn the compass card as you change the direction of the aircraft. So it's going to want to stay in that same position. Remember a few slides back there, we were talking about gyroscopic inertia. So that's how it wants to stay facing one direction. So if you do a 180-degree turn, a good way to think about it is just that gyroscope wants to keep your heading indicator pointing that same direction. So it's going to flip that compass card around, and you've just got that nice complicated gear system to make sure that gets turned into rotation this way. Because obviously, if you just roll the plane and you point yourself at the ground, you don't want that to be messing with your indications. Yeah. So this here is an important note. So it's not north-seeking. It's not going to correct itself for you. So you need to synchronize it with your magnetic compass during and before your flight. And then that was a joke from a while ago. Yeah, never mind. Anyway, here we are with our errors for the heading indicator. So precession, as I mentioned, friction will cause it to precess, have that precession error, and you get about 3 degrees every 15 minutes. As I said, every 15 to 20 minutes, you want to check your heading indicator and see if you need to correct it, because this is it's an approximation. It's not definite, but it does become noticeable over time and can lead to you overshooting your location by several miles in some cases, even on short cross countries. Limitations. Vacuum operated gyros can't be used during takeoff because there's a lot going on and they haven't had time to get up to altitude yet. So when I was flying Cessnas on power, we did have our own suction generators, and you could test them and everything and make sure they were in an appropriate range, but they weren't accurate. They weren't considered very accurate until we were up at altitude. Oh, that was not meant to go. All right, so a heading indicator will give incorrect readings beyond a bank angle of 85 degrees and must be reset afterward. This is not really a factor because you shouldn't be banking beyond 85 degrees in a Cessna 172, but if that does happen, just be aware that your heading indicator is going to be completely inaccurate, not usable. You're going to have to fly straight and level and check your compass indication, your compass heading to correct it. Attitude indicator. This is also known as the artificial horizon, and you may have seen it look like this. Sometimes it's got a little plane, and sometimes the ground here is green, but this is pretty straightforward. You've got the sky, which is blue, and then you've got the ground area here. If you want to fly straight and level, the machine is going to be calibrated so that this white line here, well, these two white lines, this white line, which represents your horizon, and the wings of your aircraft are all lined up right in the very middle. When that happens, then you know that you're flying straight and level. This is pretty straightforward stuff. Yeah, so this will tell you how much you're banked rather to either side. So you can see here you've got 0 degrees, obviously, if this yellow arrow is pointing right up. You've got 20 degrees, and then you've got 30 degrees, all the way down to 60. 60 is the very most really that you can safely turn, but 45 is kind of the most that you'd want to do in any normal circumstances. Functions much the same. It's got that gimbal to keep track of your rotation, and it's going to translate that into motion here. So bank incurs similar reactions to what happens when you go up or down. So that is to say that this little yellow part, which represents the aircraft itself, you're going to see it kind of react with your aircraft. And in general, this is in real time because it's reacting to gravity and the motion of your aircraft. So as you nose up, you're going to notice that this artificial horizon, you're going to see the horizon go down, and you can see it go up if you point your nose toward the ground. So you'd see more of the ground there. Pretty straightforward stuff. Turn and slip indicator. Wow, those are awful pictures in full screen. I apologize. That's not going to be very helpful. Anyway, this is what it looks like. This is a good picture. There's one in a glider. There's one in a Cessna. There's one in most aircraft. Basically, how this works is It's another indicator that's going to take the direction and the rate of turn of your aircraft and figure out if you are in a stable turn or if you're slipping or if you're skidding. So slipping and skidding are when you're applying too much or too little rudder and you're not synchronized with the airflow as you turn your plane or your aircraft. Sorry, just small correction. They are in Cessnas, they're not in gliders. We have a yaw string in the glider, and that operates a little bit differently. Just a continuation of this here. This is what we have in the Cessnas in general, and some of the gliders have this more basic version, but not many of them. So the ball is controlled by gravity. This ball is very heavy. It's suspended in a fluid, and it's just going to point toward the ground. So if you tilt your plane in one direction, that ball is going to go toward the ground relative to how it feels gravity. So if you're in a coordinated turn, gravity is going to be acting straight through you if you're doing it properly. So it should be pointing straight to the ground, even though you might be banked like this. As long as you're pulling up at the right angle, that all the numbers will line up, the math works out. The physics behind that is really cool stuff. Once you get into grade 11 and 12 physics, ask your physics teacher to go over it. It's really exciting stuff. I like it quite a bit. Yeah, so your turn needle has it's affected or actuated by a gyroscopic wheel behind it, which is at about 9,000 RPM, but that varies from instruments. This is the turn coordinator and your slip indicator. So these two get combined into this, if that makes sense. Yeah, so that is the end of this part of the lesson. Yeah, so thank you all for attending, and I hope you review this, you take this information into consideration, and I will hopefully see all of you again in the next lesson.